Welcome to Summarize Science. Today, we're diving into one of the biggest mysteries in astrophysics. Where do high-energy neutrinos come from? These ghost particles from deep space travel for billions of years, passing through planets and stars as if they weren't there. Because they're so hard to detect and their origins are hard to pinpoint, finding their sources is like a cosmic detective story. This new research paper presents exciting evidence for a link between these cosmic ghosts and violent flares from distant radio sources. The researchers used data from two incredible projects. First is IceCube, a massive telescope buried a mile deep in the Antarctic ice, designed to catch the faint flashes of light from rare neutrino interactions. The second is the Very Large Array Sky Survey, or VLASS, which maps the entire northern sky in radio waves, looking for objects that change over time. The central idea was to cross-reference the two datasets. They looked at a catalog of high-energy neutrino events from IceCube and searched for any flaring radio sources within the neutrino's estimated patch of sky. But they added a crucial ingredient: time. They specifically looked for radio sources that were in the middle of a flare-up around the same time a neutrino was detected. And here's the fascinating result. When they only looked for sources in the right place, the number of matches was consistent with random chance. However, when they required the radio source to be flaring at the right time, they found a statistically significant excess of matches. They found more associations than a random background would predict, with a confidence level of over 97%. This is a strong hint that a real physical connection exists. What's more, the vast majority of these flaring radio sources were not detected by X-ray or gamma-ray telescopes. This suggests radio surveys can find potential neutrino sources that are otherwise hidden from our view, perhaps because they're shrouded in dust. The researchers estimate that these flaring events could be responsible for producing about 13% of all the astrophysical neutrinos that IceCube observes. So, let's recap the key points. By combining spatial location with timing information, this study found compelling evidence linking high-energy neutrinos to flaring radio sources. This not only identifies a potential major source of these mysterious particles, but also highlights the unique power of radio astronomy in this hunt. These findings open a brand new window for tracking down the universe's most powerful particle accelerators. And the story is only just beginning. The researchers predict that with more data coming from the next phases of the VLASS survey, this hint could grow into an even stronger signal. And with a future, more precise neutrino catalog called IceCat-2, it could even reach the gold standard for a discovery. We may be on the verge of confirming a major source of the universe's ghost particles. Thanks for watching Summarize Science.